Hi, I'm Rich with Inside HPC, and I'm here at the Portland Group with Michael Wolfe. He's a compiler engineer, and we're here today to talk about heterogeneous computing, heterogeneous programming, and all kinds of other things. But let's start there. Michael, what's the difference between heterogeneous computing and heterogeneous programming?
Good question. So the difference, well, it's like flying. You can say you fly a lot, but it means different things whether you're a pilot or a passenger. Now, you can do heterogeneous computing. You can use a library, an application that's been optimized to use heterogeneous systems, but don't fool yourself into thinking that you're a heterogeneous programmer. The guy who wrote that may have done a very good job, and if that solves your problem, that's great. You don't need to do that programming. But if you do, you need to pay attention to the programming aspect of these heterogeneous systems.
You know, maybe not so long ago, a heterogeneous system was pretty exotic. I'm thinking, where would you even get access to one? But now, just about any laptop kind of has that environment built in, doesn't it?
Well, so you say exotic, and we could go into a long discussion about how exotic they are. Certainly your cell phone is a heterogeneous systems, and those things are ubiquitous. Mm-hmm. But in the HPC market, they have come and gone. You certainly recall the attached processors back in the 1970s and 80s. And today they've come back with GPUs. Would be the prime example of a heterogeneous system. And we're going to see more examples of these things coming up. Intel with their mic going to be used and programmed as a heterogeneous system. AMD APUs, even the Convey with their FPGA implemented accelerator, one can view as a heterogeneous system. So I think for obvious reasons, power and other reasons, I think we're going to see more of them in this space.
So, Michael, you work with this stuff every day, and heterogeneous programming has a rep for being hard. Is that fair?
It is hard. Well, programming is hard. If it were easy, your postman would be doing programming. Not to say the postman can't do programming, but everybody would be doing it. Parallel programming is even harder, and I've made that point many times over the past few years. And so heterogeneous programming only adds to the complexity, because now you're not only dealing with multiple different things, with multiple things, they're different, and you've got to decide not only how to do this in parallel, but where to do each particular activity.
So, you know, to take the complexity out, right, we add these levels of abstraction, but what's the right level?
This is really hard. So I'm quoting Kathy Yellick, who was quoting somebody else, and I don't know who originally said this. You have to decide what you're going to virtualize. And one of the things that makes these systems so very hard is actually not just the parallelism, but the memory. Today, all these systems have separate memory. They may actually be the same physical memory, but they have different access patterns to it. Usually, it's actually separate physical memory, and so now you have to take your data and make sure it's in the right place. So either the host or the accelerator or your heterogeneous element can get to it. And God forbid you have two of these accelerators on there. And so now you have to deal with, well, now you're dealing with data distribution. This is a problem that HPF we know solved so well, which is why it was so successful. So what's the right level of abstraction? That's a really hard problem, and I think we're going to approach that in several different ways. The deal of what do you virtualize? Can you virtualize the separate memory? The way that virtual memory virtualizes the limited physical memory on a system. Well, it's probably not going to be that easy. Because it's a performance-sensitive aspect of your program. You need to expose some things that are going to be performance-sensitive so they can be optimized, so that people can tune their program for that piece of the architecture, for that aspect of the architecture. So what's the right level? We want it to be as high a level as possible. We want it to look like natural programming as much as possible. But I think we're going to be adding some things, particularly to deal with the separation, to deal with the memory constraints, and to deal with the asynchronicity between the host and the attached device.
So how do you go about doing that? What are the methods for heterogeneous programming?
You know, so we've seen many of them come and go. The ones that are most talked about in the HPC space today, we'll start with CUDA. There's now the granddaddy of them all. It's all of 5 years old. Followed on very closely by OpenCL. And they have a basically almost uniform model of what the attached device looks like. They expose the separate memory. They expose the asynchronicity between the devices. They're both reasonably low-level models, which gives you a lot of control, and you can do a lot of tuning at that level. What you lose is performance portability. because you need to tune it so much for that device that if you want to move to a different device, you're going to need to retune your program. OpenCL is actually a very, very low-level model, and I think we need something on, it was intended to be a low-level model on top of which something else was built, and we haven't seen this something else yet. Maybe we'll move in that direction. Microsoft has proposed C++ AMP, which is very interesting. I think it's perhaps gone a little too abstract. I'm not a big fan of C++ classes as an abstraction level solution to all problems. I'm willing to be proven wrong there. Google's proposed RenderScript. RenderScript is really targeted at a specific style of program. It's the graphical programming in embedded systems. So think if they want to do some graphics processing on your cell phone. But then they're also saying it can be used for other sorts of heterogeneous programming as well. And I don't think it's a very good solution in there, but I'm willing to be proven wrong there. And then there's some directive-based models. There's the PGI accelerator model, which is several years old, and then the more recent OpenACC, which we think is a step in the right direction. Intel has proposed their offload model for their use on the mic, and I think that's pretty much directed at a target architecture that looks like mic, so it's unclear whether that's going to preserve performance portability. So there's a lot of options there, and I think we need to explore those. I think to put a dig at the academic community, they haven't stepped up to the plate and really explored how we should be programming these systems.
Yeah. So it sounds like these things are solving the problem of heterogeneous computing, but very specifically to a platform. Is that fair?
Mostly that's somewhat true in some cases. I would say Microsoft would argue C++ AMP is more general. OpenACC would argue it's more general, but it's targeting a certain class of applications, a certain style of application programming. So I don't think we've seen the perfect general model yet, but I'm not sure we're going to find a perfectly general model. I don't think parallel programming is hard, and you're going to tune your parallel programming model for a certain style of application.
Absolutely.
And these devices actually, if you look at the parallelism on the device, you've got these multiprocessor parallelism and you've got vector parallelism. So a lot of applications don't take advantage of vector parallelism. And if you can't, you're going to lose a factor of performance. You try to take advantage of that device. And the programming model isn't going to help you there.
So at the recent SC11, I was there, and Addison Snell chaired this meeting where he counted 12 different heterogeneous kinds of platforms that are out there.
Cool. In HPC.
In HPC, just in HPC.
I'm impressed.
Which ones are going to survive?
That's an interesting question. It's as much a business question more than a technical question.
Yeah.
Right? So good technical solutions will die for various reasons. If you look at, say, ClearSpeed, and I don't know technically whether it was a great solution, but they were solving a good problem, and it was focused at HPC, but there's not much of a market in HPC. You know, as someone said, it's a $0 billion a year market. So how do you survive when the cost of developing a chip, Intel and NVIDIA would tell you, the cost of developing a chip is $1 billion, and they haven't sold anything yet. So you need to address this, your chip design, to target a larger market than that. Or to have enough cash that you can subsidize this market. And that's not a long-term solution. So I would say GPUs are going to survive because they've got a market that can support the chip development, and it's unclear anybody else will.
Yeah. So Pete Ungaro today was quoted, I think he was at some conference somewhere, that we're going to be seeing computers with 1 billion processing elements, billion threads, you know. Is that the kind of thing that keeps you up at night, worrying about?
No, it doesn't. So the billion is a false number, right?
Yeah.
I mean, if we were to count all the computing elements in a 12-core AMD Opteron, or Barcelona, or Bulldozer, whatever it is, well, it's not just 12 because they have all these SSE processors, and there's 4 of those, so it's 48 all of a sudden. And so when you count CUDA cores, that's the kind of number they're counting, is each one of those floating point processors turns into a core. So these things get agglomerated or aggregated is the right word, into some number. So the billion probably turns into 10 million. And that's a number I can deal with.
You can deal with that. You can actually
Visualize
that.
I'm thinking we're going to see on the order of a chip will be a 10 petaflop device. Sorry, 10 teraflop. 10 petaflop would be pretty good.
Yeah.
A 10 teraflop device will have 100,000 of those. So the number of nodes is not going to be on the order of more than 1 million.